Now that we have some feel for the hyperbolic plane, I want to have a change of pace and talk a little bit about maths history. For us, the story begins over 2,000 years ago in ancient Greece. At this time, there were many great mathematicians, philosophers, and natural philosophers throughout the ancient world, particularly in Greece and the Eastern Mediterranean and across through to Asia. Around 300 BCE, a mathematician called Euclid sought to amass the world's knowledge of mathematics in a single work, his Elements. This included some number theory and solid geometry, but the bulk of it was plane geometry, which is why we call the standard two-dimensional plane the Euclidean plane. What makes the Elements unique among the wealth of mathematical treatises available at the time was his novel approach. He wrote down just 5 basic principles of plane geometry, which are supposed to be self-evident, irrefutable, and most importantly, not derivable as consequences of simpler principles. These are called Euclid's 5 postulates, or axioms. We assume that they are true, or declare them to be true depending on your point of view, and then derive all other knowledge as a consequence of these postulates. This approach was radical and anticipated the modern formal approach to mathematics, which began in the late 19th century, by 2,000 years. Euclid's 5 postulates are as follows. A straight line segment can be drawn joining any 2 points. Any straight line segment can be extended indefinitely in a straight line. Given any straight line segment, a circle can be drawn having the segment as a radius and one endpoint as its centre. All right angles are congruent, where a right angle is defined as what you get when you bisect a straight line. And finally, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. Certainly, I hope you'll agree that the first 4 postulates are self-evident, irrefutable, and unlikely to be derivable from simpler principles. However, the 5th postulate stands out. It doesn't look simple or self-evident. You probably have to draw a picture to work out what it's even saying. And its complexity does suggest that you might be able to derive it from simpler principles. The 5th postulate is mathematically equivalent to what is known as the parallel postulate, which may be slightly easier to parse. If you have a line and a point not on that line, then there is at most one line through the given point which is parallel to the given line. The natural question becomes, is it possible to derive the 5th postulate from the other 4 postulates, or is it indeed an independent, necessary axiom? For 2,000 years, the greatest mathematicians, including Euclid himself, tried to solve the problem. No one was able to derive the parallel postulate from the first 4 postulates, but this is not a proof that it's completely impossible. If you suspected that the 5th postulate could not be derived from the others, how would you go about trying to prove this? One of the best ways would be to find a different sort of geometry, one in which the first 4 postulates held true, but where the 5th one was false. This would mean that you can't derive the 5th one from the first 4, because if you could, the 5th one would have to be true in every geometry where the first 4 are true. This problem remained unsolved until, in 1829, the Russian mathematician Nikolai Lobachevsky discovered the hyperbolic plane, sometimes called Lobachevsky space in his honour. In the hyperbolic plane, the first 4 postulates are true. Pairs of points give line segments. Line segments can be extended to give lines. Line segments can define circles. And all right angles are congruent. However, the parallel postulate and therefore the fifth postulate are false. Remember that the parallel postulate says that if you have a line and a point which does not lie on that line, then there is at most one line through the point which is parallel to the given line. We can see that this is not true quite easily using the Poincare disk. So here's a line, and here's a point not on that line. Now there are multiple lines through the point which do not meet the given line and which therefore are parallel to it. In fact, there are infinitely many. This means that you cannot derive Euclid's fifth postulate from the other four. It is a necessary axiom of Euclidean geometry. Let's return to the major themes of this course: symmetries, isometries, and periodic tilings. After the last video, it may not surprise you that the philosophy which we derived in the Euclidean plane and applied to the sphere ports over to the hyperbolic plane directly. We have a notion of distance on the hyperbolic plane. I haven't given you the formula for the distance because it's quite complicated, but remember we never really used the formulae for distance in either the Euclidean plane or on the sphere, so this shouldn't be too much of a problem. We can then define an isometry of the hyperbolic plane to be a transformation of the plane which does not change the distances between points in the hyperbolic way of measuring distance. A symmetry of a shape or pattern in the hyperbolic plane is an isometry of the plane which leaves the shape or pattern looking the same. As always, we have the identity transformation which sends each point of the hyperbolic plane to itself. This clearly doesn't change distances and is a trivial symmetry of every possible shape or pattern. What about reflections? We'll first look at a line like this on the Poincare disk. If we reflect the disk in this line in the normal Euclidean way, every point of the disk gets sent to another point of the disk. And hopefully you can believe me that it doesn't change the distances between points as measured using the strange hyperbolic measuring system. What about reflections in lines like this? This is also possible, and actually not too hard to do, or even write down a formula for how it works. But for the sake of brevity, I will spare you the details. If you're interested, you should look up circle inversions, which is the general way that mathematicians define what it means to do a reflection in a circle or arc of a circle. If you have been following along with the exercises for the previous videos, you will know that the following theorem is true for both Euclidean and spherical geometry. Theorem: given two labelled congruent triangles, A, B, C, and A', B', C', there is a unique isometry which sends A to A', B to B', and C to C'. This is also true in the hyperbolic plane, and the proof is identical to the proof in the Euclidean plane and on the sphere. Moreover, this proof demonstrates that every isometry of the hyperbolic plane can be broken down into a sequence of at most 3 reflections. We can use this to find all possible isometries of the hyperbolic plane in the same way that we did this for the Euclidean plane and the sphere. If there are 0 reflections, you have the identity, and 1 reflection gives you a reflection. If you have 2 reflections, then there are 3 possibilities. If the lines intersect somewhere in the hyperbolic plane, doing the 2 reflections produces the hyperbolic equivalent of a rotation. If the 2 lines are parallel like this, it turns out to be an elementary fact in hyperbolic geometry that there is exactly 1 line which intersects both lines at right angles. Doing 1 reflection and then the other gives the equivalent of a translation in the hyperbolic plane along this orthogonal line. The third possibility lives between these 2 extremes, and that's when the 2 lines are like this. These two lines only meet at infinity and don't meet in the hyperbolic plane, so they are still parallel, but they are parallel in a different way. Doing one reflection and then the other gives an isometry like this, which looks either like a rotation centered at infinity or a translation along a circle like this. To differentiate these three different isometries, the first one is called elliptic, the second one hyperbolic, and the third one parabolic. The final possibility is that you have three reflections, and in this case what you get is the hyperbolic version of a glide reflection, a combination of a hyperbolic isometry and a reflection in this line. We've finally made it to discussing tilings of the hyperbolic plane. We've already seen one tiling with equilateral triangles meeting 7 around each corner. Just as on the sphere we could get equilateral triangles with angles of any reasonable size we like, which is bigger than 60 degrees, you can get equilateral triangles with any size you like less than 60 degrees in the hyperbolic plane. So there are tilings with 7 around a point, 8 around a point, all the way up to and including infinitely many round a point. To get infinitely many round a point, all of the angles need to be 0, and amazingly, this is possible in the hyperbolic plane if the corners of the triangles are all at the boundary of the Poincare disk at infinity. What about other regular tilings? Well, pick any number of sides you like and any number of tiles around a corner that you like. And if it doesn't give you one of the 8 regular tilings of the sphere or Euclidean plane, there is an appropriate tiling of the hyperbolic plane. 4 hexagons around a point, 3 heptagons around a point, even infinitely many infinigons around a point. Anything is possible. There are all sorts of other non-regular tilings you can come up with. You can analyze their symmetries in the same way that we analyze the symmetries of spherical and Euclidean tilings. We can find fundamental domains for the groups of symmetries of these tilings, find sets of generators, lists of features in the tilings that give us the name of the group of symmetries, and so on. As before, each of the features comes with a cost. For the Euclidean plane, the cost always added to exactly £2. On the sphere, it's always cheaper than £2, and perhaps unsurprisingly on the hyperbolic plane, it's always more expensive than £2. Unfortunately, you do have to be careful. If you go shopping and pick out a random selection of features costing over £2, it is possible that they don't go together to give you a real tiling of the hyperbolic plane, so you have to choose your features carefully. I want to tie all of this back to our study of the sphere and the Euclidean plane. At the start of the last video, I showed you this table. Now when you looked at that, perhaps you spotted that there are some entries missing. And now if I add a column for the hyperbolic plane, we can fill in some of those gaps. What you'll also notice is just how similar the hyperbolic plane is to those other two spaces. All three are two-dimensional. Shortest paths on the hyperbolic plane are arcs of circles. All isometries on the hyperbolic plane are generated by reflections, and you just need 3 of them to get any isometry you like. On the Euclidean plane, we had 5 isometries: the identity, reflections, rotations, translations, and glide reflections. On the sphere, translations got lumped in with rotations. On the hyperbolic plane, actually translations come in 2 different varieties, so there are 6 isometries in total. There are only finitely many regular tilings represented on the sphere or the Euclidean plane. All infinitely many other theoretical regular tilings are possible on the hyperbolic plane. Similarly, there are also only finitely many wallpaper groups on the sphere and Euclidean plane, and the hyperbolic plane takes up the slack, adding infinitely more. The last 2 properties I'll mention are the Conway cost and the triangle angle sum. On the Euclidean plane and sphere, we could spend up to £2, and the hyperbolic plane allows us to go up beyond £2. And if we want triangles on the sphere or Euclidean plane, the angle sum has to be greater than or equal to 180 degrees. But on the hyperbolic plane, we can get any angle sum we like down to and including 0 degrees. We started off this video, and indeed this course really, with Euclid, and we have finally arrived at Escher. M.C. Escher was an artist born in 1898. He wasn't a trained mathematician, but he was always captivated by the beauty of mathematics and often incorporated mathematical ideas or objects in his work. Of particular relevance to us is his series called Circle Limit from the late 1950s and early 1960s. These are artworks taking the form of tessellations of the hyperbolic plane, and the most famous is perhaps Circle Limit 4, better known as Heaven and Hell, or Angels and Demons. Let's look at this perhaps slightly less well-known Circle Limit by M.C. Escher, Circle Limit 3. You can see the pattern is based around fish, but also at a glance you can see that it is a tiling of the hyperbolic plane. If for a moment we ignore the fish, you can see that he's actually given us a tiling using the white lines, which are straight lines in the hyperbolic plane. The tiling is broken up into a number of squares and a number of triangles. And you can see that the underlying tiling is actually the same as this one here. So at each of the corners there are 3 squares and 3 triangles which meet. Also interesting, before we analyse the symmetries of this tiling, look at the colours of the fish along the hyperbolic lines. Pick a hyperbolic line, all of the fish have the same colour. Let's work out the symmetry group, and we'll ignore the colours of the fish for our purposes. The first task is to find a fundamental domain. If we look at just the underlying tiling of squares and triangles, this is a fundamental domain. But this tiling has lots of reflectional symmetries, but the patterns of the fish break those reflectional symmetries, so in fact there are only rotational symmetries. So this fundamental domain is not a fundamental domain for the pattern of fish. You can check that in fact this is a fundamental domain. The way to convince yourself of that is that it more or less captures one fish, and every fish is in fact a copy of this one fish. So now that we have a fundamental domain, we can try and spot centres of rotation, reflection, glide reflections, all these kinds of things. I've already said there are no reflectional symmetries, and so there are also no glide reflectional symmetries. But we do have centres of rotational symmetry, and each of the 4 corners of this fundamental domain is such a centre. One of the centres is in the middle of a square, and that gives us 4-fold rotational symmetry, again remembering that we're ignoring the colours. Another is in the centre of a triangle, and that gives us 3-fold rotational symmetry. The other 2 centres are where the white lines intersect, and you can see that at each of those points there are 3 heads that meet and 3 tails that meet. So in fact these points again have 3-fold rotational symmetry. Using Conway's notation, we can write down this symmetry group as 4, 3, 3, 3. We can also work out the Conway cost in the normal way, and this is the answer. This is the end of this London Maths Outreach course on symmetries, and indeed the end of London Maths Outreach courses for this academic year. Albert and I do hope that you have enjoyed coming on this journey into a beautiful part of mathematics, and one which is unfortunately normally hidden from people outside of a maths degree. Even though we've spent 4 weeks looking at these sorts of geometries, we've only been able to scratch the surface of what is out there, and there's so much more to explore and understand. But this course and this video must end, and so I shall say goodbye.